Hello everyone, I am Aniket Koul and today we'll be discussing the 24th problem on the CP-31 sheet by TLE Eliminators under the 1200 problems. So now let's move to the CP-31 sheet and we can see that the 1200 parameter has been checked. We'll be scrolling down to find my 24th problem, Palindrome Game. Let's begin. Now the problem statement is as follows. First of all, it is given that it's an easy version, right? And now the problem states as follows. A palindrome is a string that reads the same left to right and right to left. For example, 101101 is a palindrome while 0101 is not. Now Alice and Bob are playing a game on a string S, which is initially a palindrome in this version, of length n, consisting of the characters 0 and 1. Both players take alternate turns with Alice going first. In each turn, the player can perform one of the following operations. Choose any I from 1 to n where s of I is 0 and change s of I to 1 by paying $1. Right. Or the other operation could be reverse the whole string, pay $0. This operation is only allowed if the string is currently not a palindrome and the last operation was not reverse. That is, if Alice reverses the string, then Bob can't reverse the string in the next move and vice versa. Reversing a string means reordering its letters from last to the first. For example, 01001 becomes 10010 after reversing. The game ends when every character of the string becomes 1. The player who spends minimum dollars till this point wins the game, and it is a draw if both spend equal dollars. If both players play optimally, output whether Alice wins, Bob's wins, or is it a draw. Right. Now the input format and the constraints are as follows. The first line of the test file will contain a single integer t denoting the number of test cases, which can range from 1 till 10 power 3. Then for each test case, the first line would contain a single integer n denoting the size of a string, which can also go up to 10 power 3. Now the following line of each test case would contain a single string s of length n, which contains only the characters 0 and 1, and it is guaranteed that the string s is a palindrome and contains at least 1 0. Now note that there is no limit on the sum of n overall test cases. For the output format, we have to print Alice if Alice wins the game, or Bob if Bob wins the game, or draw if the game ends in a draw. Right. Now, as you have read the problem statement, we can move on to understand it. So, for every test case, it is given that we have two things, n and s. N is an integer, right? And it denotes the size of our string s. So, s is a string and n denotes the size of it. It is also mentioned that s is a binary string. So, it contains only the characters 0 and 1, right? Also, for this version of the question, as you could read, it was the easy version. For the easy version, it is given that S is initially a palindrome, right? So, as mentioned in the question, a palindrome is a string which is same when we read it from left to right or from right to left. For example, if we have a binary string which contains only zeros or ones, 101 is a palindrome. A single character is always a palindrome, either 0 or 1, and 1 1 is also a palindrome. 1001 is also a palindrome, so on. Right? All of them read the same from left to right or right to left. Now comes the operations. Now two people are playing, Alice and Bob. So what happens is Alice moves first. In every move, what either player can do is either take any s of I such that s of I was initially 0 and convert that 0 to a 1, right? And the player who made this operation has to pay $1. He has to pay $1 to do this operation. Otherwise, what the player can do is just reverse the string. These are two types of operations, A and B, but there are some restrictions on the second operation. So the first restriction is that when you are trying to reverse the string, S should not be I should not use a not equal to sign, but S should not be a palindrome. This is the first most important condition. S should not be a palindrome. The other condition is that the previous operation should not be reversal. So these are the two conditions that must be satisfied in order to perform the second operation. For the first operation, there is no special condition. You can always perform it, given that there are at least 1 zeros. Otherwise, if you want to perform the second operation, you must satisfy both these conditions, and only then you can perform the second operation. And the second operation is free of cost. It does not cost the player anything. Now, these operations are continued until there are no zeros left. So once all the zeros in the string have been converted to ones, the process ends. And at the end of the process, Alice might have spent some X dollars and Bob might have spent some Y dollars. So if X is less than Y, that means if Alice spends less, you have to print Alice. If X is equals to Y, then both are spent equal. So you print draw. And if if X is greater than Y, that means Alice has spent more than Bob, then you just print Bob. Basically, whoever spends the lesser amount of money wins, and if both spend the same amount, etc. Now, as we have understood the problem statement, let's move on to seeing some sample test cases so that we understand the problem better. Now, let's see the first one. And let's also increase the font size so it is better visible. Right. So this is our N and this is our S. As we said, Alice moves first. So what Alice could do in the first operation, obviously, Alice can't reverse the string because the string is already a palindrome. So she must use the first operation to convert some 0 to a 1. So let's say this is 1001. Let us index it 1, 2, 3, 4. So let's say she changes the second index. So that means this 0 to a 1. So that makes it 1101. Right. Now this string is no longer a palindrome and the previous operation was an order reversal. So what Bob can do is reverse this. So 1011. Right. And now the previous operation was reversal. So Alice can't reverse it again. So she has to uh, convert this lone 0 to a 1. So that is 1111. And all the operations, that means all the zeros have been converted to ones. So there are no more zeros left in this string. So our operations end. And we can see that Alice used up $1 here. And she also used up $1 to convert this 0 into a 1. So here as well. But Bob did just one reversal operation, which is free of cost. So that means x is equals to 2 and y is equals to 0. As x is greater than y, we print Bob. As simple as that. Right. Now, please remember the question. It is said that both Alice and Bob play optimally. So we'll have to look out for that. Now, let's move on to the expiry time complexity. It was mentioned in the question that there is no bound of n overall test cases. So we would have to write our time complexity as O of t into some function of n. which means that if we consider our number of operations limit to be 10 power 8, which is also the number of operations that we can run in 1 second on Codeforces, then if we see that t can go up to 10 power 3 and n can also go up to 10 power 3. So which also means that O of t into n would take about 10 power 6 operations. O of t into n square would take up about 10 power 9 operations. So you could see that O of t into n works fine within a 10 power 8 constraint, but O of t into n square does not. So what does O of t into n and O of t into n square mean? That in this case, we are running per test case in O of n, and in the second one, we run in O of n square per test case. So O of n plus test case per test case works because that comes out to be in total 10 power 6 operations, which is well within our limit. But O of t into n square, which is same as O of n square per test case, does not work. So we want our expected time complexity of the algorithm to be somewhere here, right? O of t into n. So now let's discuss the solution. Now before discussing the exact solution, let's make some observations which will help us uh, to guide ourselves towards the actual logic, right? So let's consider few cases. So for the first case, before considering the cases, let us discuss one thing, that we can either change a 0 to a 1 or we can reverse, right? Now this operation does not change the number of zeros and ones, right? So let's ignore this for a second. But this operation always decreases the number of zeros. So it decreases number of zeros, right? So now that means that our logic should always be considering the number of zeros as the main factor towards the winning or the losing cause, right? So number of zeros will always be a major factor. We will see that the ordering of the zeros, that is at what positions they are present in our string, won't matter. We'll discuss that and we'll prove that as well. But we are for sure at this point that number of zeros do matter, because at every operation either we will reverse the string or convert 1 0 to a 1, right? So number of zeros should be considered. Keeping that in mind, let's discuss some cases. So for the first case, I would say that what happens if the number of zeros in my string s are even. Let's discuss this case. If number of zeros in my string s are even. Now, if number of zeros are even, what Bob can do is as the following. The first operation will belong to Alice. Now in the first operation, S is already a palindrome as given in our problem statement, that in the beginning S is a palindrome. So as S is a palindrome, we cannot reverse it, or that means Alice cannot reverse it. So in the first operation, Alice has to pay $1 and change some 0 to 1. Correct. Right. Now, can we prove that after converting any 0? So now I am saying that Alice can convert any 0 to 1, but can we prove that after converting any 0 to 1, the new string S would not be a palindrome for now? Can we prove? So let's see, how can we prove that? Let's firstly see a case where converting a 0 to a 1 would still keep our S as a palindrome. Let's see. Now, if we think properly, we can say that converting a 0 to a 1 would still keep S as a palindrome only if that converted 0 was present in the middle, right? So we had, let's say, some k number of characters here, this 0 here, and some k numbers of characters here, right? So if we still converted, so if we consider that this string was already a palindrome, even if we convert this 0 into a 1, the new string will also be a palindrome, right? This is the only case. Why? Because let's say you convert some 0 which is not in the middle, right? Let's say you convert a 0 which is present at some index I, which is not the middle index. So what would happen is that at the index s of n minus I plus 1, right? Because these, because in a palindrome, s of I and s of n minus I plus 1 are always equal, right, in a palindrome. So if s of I was 0, then s of n minus I plus 1 would also be 0. But if you convert this 0 to a 1, this is still 0, and now it breaks the condition of a palindrome. So we can say that this string is no longer a palindrome, right? So which also means that it is only possible to change 0 to a 1 while still maintaining the palindrome property only if that 0 is present in the middle. But if there is a 0 present in the middle, then we would always have odd number of zeros. Again, why is that? Because if 1 0 is in the middle, for every other index, right, they would always form a pair. So the first index would form a pair with the last index, the second index would form a pair with the second last index, and so on, right? The ith index would form a pair with n minus I plus 1th index, except the middle because it forms a pair with itself, so that you can consider it alone. But all other indices would form a pair with some other index. So that means if you ignore this 0 for once, there would be even number of zeros, right? And then adding the 0, there would be odd ones. So we can say if there exists a 0 as a middle character, then we would always have odd number of zeros. But which is not possible because we are considering the case where zeros are even. So we can say that no matter at what position we change the 0 to a 1, our string will not be a palindrome. Which also means that after Alice plays a move and uses a $1, Bob can reverse, right? Bob can reverse. But will he? That is the question. Well, we don't, or Bob does not need to be greedy here. He does not need to reverse at this position itself. I'll show you there is a even better strategy. So what Bob can do is keep playing the game and also pay $1. Okay. So be with me currently. Alice pays $1, changes some 0 to a 1. Bob pays $1 and changes again some 0 to a 1. Now Alice and Bob keep doing it, right? And Alice on the third step still has to pay $1. She still does not have a choice. We'll prove that as well. So we proved earlier that if zeros are even, if number of zeros are even, then there cannot exist any middle 0, right? So if there does not exist any middle 0, let's say Alice took some index I and changed s of I to 1, where s of I was initially 0, right? It was initially 0. She changed this to 1. So what Bob can do on the other step, he can change s of n minus I plus 1, where I is from the previous operation. He can change n minus I plus 1 to 1 again, because initially s of I would be 0, because they both come in pairs in a palindrome. So Bob can change n minus I plus 1 in his operation. And after the second operation, S will become a palindrome. Why is that? Because before the first operation, S was a palindrome. You changed some 0 to a 1, and then Bob changed the pair 0 to 1. So again, it becomes a palindrome. So on the third step, Alice does not have a choice to reverse because S is currently a palindrome. So she has to still pay $1 and again convert some 0 to a 1. So now Alice pays $1, Bob pays $1. Again, Alice pays $1. Again, Bob will pay $1, and this game will continue until until there is only one zero left. So if there is a single zero left, then we'll see what happens. So let's say there are 6 zeros in the beginning. So Alice converted 1 0. So after this operation, only 5 zeros are left. Alice converted a 0 to a 1, then only 4 are left. Now after this operation, only 3 zeros are left. After this operation, only 2 zeros are left. Right. Now Alice again, as I said, will not have a choice but to convert another 0 to a 1. So after this operation, 1 0 is left. But if only a single 0 is left, and as I said, there is no middle 0, then this string is definitely after Alice's operation not a palindrome, right? As we proved earlier, it can never be a palindrome. So if it is not a palindrome, that means Bob can reverse it. So Bob will use his reverse operation now. Now as Bob has reversed the string, Alice does not have the option to reverse it because it had been reversed in the previous operation. So Alice cannot reverse it now. Hence Alice has to again pay $1. And after paying this $1, there would be 0 zeros left. Now as there are no zeros left, the operation comes to an end. And now let's see who paid how much. Alice paid 1, 2, 3, and $4. So X is equals to 4, and Bob paid 1 and 2. So Y is equals to 2. I hope I have not used X and Y anywhere else, because X and Y represent the same thing which I used while explaining the problem statement. X is the amount paid by Alice and Y is the amount paid by Bob. So Alice has paid $2 more than Bob, and hence we'll print Bob because X is greater than Y. And now you can see that this would work for all even values except 2, because in 2 what will happen is Alice pays $1. So now there is only 1 0 left. So in the first step itself, we reach this position. So Bob will simply reverse at this position itself. And Alice would have to pay $1 again. So in this case, X is equals to 2 and Y is equals to 0. But still Bob wins. Right. So in any case, Bob will follow the strategy that until only 1 0 is left, keep paying $1. So Alice has to pay $1, Bob will pay $1. Alice has to pay $1, Bob will pay $1 until only 1 0 is left. And when 1 0 is left, Bob will simply reverse. He will not no longer pay $1. He will reverse. And as he had reversed in the previous operation, Alice cannot again reverse. So she has to pay $1 and end the operation. So that would always lead to Bob winning if the number of zeros are even. So that marks up our first observation, that if the number of zeros are even, then Bob always wins. Right. We got this observation. Now we'll use this observation to quickly prove the second case where the number of zeros are odd. Right. Now, as I said in the earlier case, that if the number of zeros are even, that means we can never have a middle zero. Right. But now we'll see that if zeros are odd, the number of zeros are odd, then we must have a middle zero. Because as I said, all characters in a palindrome occur in pairs, right? So S of I should be equal to S of n minus I plus 1. Only time it does not need to occur in a pair is when at the middle position, that is the n by 2 position, we have a 0. So if we have a 0 there, then the number of zeros can be odd, right? And we can see that it is the only case, as we said earlier as well, when the number of zeros can be odd. So all other zeros will occur in pairs, and this middle 0 will be a lone character in the middle. So that would lead us to us having odd number of zeros. Now, keeping this observation in mind, let's play this again. Right. Now, what happens is that Alice will pay a dollar. Right. She does not have any uh, choice because initially S is a palindrome. What she has a what but the condition where she has a choice is to select with 0. Right. So what she'll do is select the middle 0. So as I said, at the n by 2 position. Right. So she'll select the middle 0, and now the new string S after converting the middle 0 to a 1 would still be a palindrome. Right. Because as I said earlier, you just change the middle character and still all other characters are still occurring in pairs. So this new string would be a palindrome. So now Alice, I'll write it here again. Alice pays a dollar, but the string S is still a palindrome. Right. So now Bob will have to pay a dollar. Right. Because he does not have the option to reverse it because the string is still a palindrome. Now let's see. Let's say the number of zeros are 5. After this operation, the number of zeros are 4. Right. Now after this operation, number of zeros are 3. But the number of zeros are 3, but we don't have a middle 0 for now. Right. Because the middle 0 is converted to 1 in this operation. So Alice can choose some 0 such that the string again becomes a palindrome. Can't she? Because as I said, there is no middle 0 for now, and we have odd number of zeros. So that means at least for 1 0, it is the case that S of I is 0 and S of n minus I plus 1 is a 1. Right. So after this operation, this is the case for at least 1 0. That this has been converted to a 1, but this is still 0. So Alice can now convert this 0 to a 1 and again make the resulting string S a palindrome. So after this operation as well, our string would be a palindrome. Now what Bob will do, he will have to pay a dollar and only 1 0 is left. Right. But now there is only 1 0 left and it is not the middle 0. That means the string S now is not a palindrome. So what Alice can do is simply reverse. Right. Alice can reverse because the previous operation, no reverse operation was performed and the string S is not currently a palindrome. So Alice can reverse and then Bob will have to pay a dollar again and convert the last 0 to a 1. So now there are only 0 zeros left. So this is kind of the inversion happening. So in the previous case, it was Bob who could reverse at any moment, but was keeping his reverse operation to the last and then winning. But in this case, you can see that Alice could reverse here, but she did not. She waited for the last opportunity where Bob had only 1 0 left, and then she reversed. So it is kind of the opposite case, and we can show that no matter the ordering of zeros in our string S, Alice can always win if the number of zeros are odd. right? But there is only one edge case, and uh, fortunately, that edge case was covered in the sample cases. So if you see this second case here, which represents the string containing a single character 0. Now, still, this is a palindrome and it has a middle 0 and it has odd number of zeros. But here, what happens is Alice will have to pay a dollar, right? And now this has converted to a 1. And now, as there are no longer zeros, the operation ends. Alice has paid $1, Bob has paid none, so Bob wins. So, this is the edge case where there are exactly 1 0 in our string S initially. So in that case, Bob wins. Otherwise, whenever there are odd number of zeros, we can prove that Alice always wins. So our final logic is as follows. If the number of zeros, let's say count 0, stored the number of zeros in our string S initially. So if count 0 is even or count 0 is equals to 1. In both the cases, Bob wins. Otherwise, Alice wins. As simple as that. So now to discuss the time complexity of this approach, we can see that we only need the count of zeros to know the answer, and hence that would take an O of n loop per test case to calculate this value. So the total time complexity would come out to be t into n, because for every test case we take n O of n time, and hence for t test cases we would take O of t into n. Now let's discuss the implementation. The implementation is also quite straightforward. For every test case, first of all, we take the number of test cases as input. Then for every test case, we take in the size of our string and the string itself as input. And then we define a count 0 variable, same as we discussed in our solution. So now this is an O of n loop where we just calculate the number of zeros and update the count 0 variable accordingly. Then again, as I said, if count 0 is even or count 0 is 1, then Bob wins, otherwise Alice wins. As simple as that. So what we can say is that the total time complexity is O of t into n, and the total space complexity would come out to also be t into n, because for every test case we are just storing the string which is O of n memory. The count 0 variable is O of 1 memory, so we don't need to worry about that, and we have to store that for every test case, so we can say it is t into n memory. So for the final remarks, I would say that this problem involved a lot of uh, observation finding and a bit of intuition as well. So these type of problems are quite common for this rating range and also for div 2b's. So uh, in competitive programming, intuition and observation based problems are also a very essential part. So I think this problem tackles that range effectively. I hope you like the solution, and thank you.